Welcome to this lesson on integer exponents. Today we're going to talk about using patterns of integer exponents and applying properties of integer exponents. The essential question for today's lesson is how can you develop and use properties of integer exponents? Please remember at the end of the lesson to write this question down and answer it on the essential questions page. So the first thing we're going to look at is using patterns of integer exponents. So if you take a look at the table, I want you to look and see if you can find a pattern that you can see in each row. And so if you want to take a minute, pause, see if you can find a pattern. When we come back, we can talk about it. All right, so I don't doubt that you guys notice that when you're looking at these, you can tell that the numbers, the answers, get smaller every time. Now, I know these are bigger numbers up here that we don't usually deal with on a day-to-day basis, but another pattern that you could have found is that as you go down the row, so here, 625, if I divide it by 5, I get my next answer. If I divide 125 by 5, I get 25. 25 divided by 5 is 5. It works the same for down here. 256 divided by 4 is 64. 64 divided by 4 is 16. 16 divided by 4 is 4. This works for all exponents. So using that thought, let's see if we can figure out what would go in this column here. So anything to the 0 power. So I want you to take a minute and try and solve these three. Right, so if I do 5 divided by 5, I get 1. If I do 4 divided by 4, I get 1. If I do 3 divided by 3, I get 1. So if I follow the patterns, I get 1 for all of my answers. These are correct. So what conjecture can we make about any number to the 0 power? What will the answer always be? Anytime you see a number to the 0 power, you know that the answer is going to be 1. So now let's take it a step further. Now we've gone from 5 to the 0 power to 5 to the negative first power. So now, if we're following the pattern of dividing every time, if I do 1 divided by 5, I know I can even do this on a calculator. So if I type in 1 divided by 5, it gives me 2/10 as a decimal. So 0 and 2/10. If I write this as a fraction, I get 2/10, which reduces to 1/5. So 5 to the negative first power is 1/5. Let's try it with 4. 1 divided by 4, that will give me 0 and 25 hundredths. As a fraction, that gives me 25 over 100. And simplified, that gives me 1 over 4. And if I try it again with 3, 1 divided by 3, that gives me 0 and 3/10 repeating, which I know converts to 1/3 as a fraction. So let's take a look then at 5 to the negative 2. So if I take 1/5, and this part you don't need to write down. If you'd like to, it would probably be helpful for you, but it doesn't have to be. If I take 1/5 and I divide it by 5, I know that this turns into 1/5 times 1 over 5, which equals 1/25. Again, 1/4 divided by 4, because we found that that's the pattern as we go down the row. We just divide each time. Again, to divide fractions, we actually multiply by the reciprocal. And then here I get 1/16. And I wonder what I'm going to get for 3. Because if you look, 5 squared is 25. 5 to the negative 2 is 1/25. And 4 squared is 16. 4 to the negative 2 is 1/16. So would it be safe to make the conjecture that 3 to the negative 2 would be 1/9? If you made this conjecture, you would be correct. Right? So what can we say is a to the negative 2? What is any number to the negative 2 power? Well, any number to the negative 2 power is going to be 1 over that number squared. So now, if we take a look, what if we make that exponent a variable? Because here we had it to the negative 1, and if you look at 3 to the first power, it's 3. 3 to the negative first power is just 1/3. Well, if this is the case, it's still going to be 1 over something, and we still have that base number to its positive or its additive inverse power. So when you're looking at negative exponents, you know that you're going to get a fraction, and that fraction is going to be 1 over the base to the positive power. So if I had a to the negative 9, my answer would end up being 1 over a to the 9th power. So your reflection question: write a general rule for the values of a to the 0 and a to the negative n based on the patterns in the table. Right? So your general rule is what we found right here. You can write that in your conjecture, that a to the 0 is always going to be 1. So any number to the 0 power is 1. And then a to the negative n, any power of any number that is a to the negative n power is going to be 1 over that number to the positive of that power. Right? So the negative just turns it into a fraction. All right, so let's take a moment and give these a shot. I know that in this case, my answer has to be a fraction because I have a negative exponent. So it's going to be 1 over something. Well, if I want to know what 6 to the 4th power is, I can multiply it out, or I can grab my calculator and type it in. 6 to the 4th power is 1,296. So remember, when we do this, we get 1 over 6 to the, and we keep the 4, but now we make it positive, which then changes to 1 over 1,296. Right. I want you to take a moment and try these on your own. Go ahead and use a calculator, and when you come back, we'll check your answers. All right, so for 12 to the 0 power, you should have gotten 1. For 8 to the negative first power, you should have gotten 1 over 8. 347 to the 0 power is 1. 15 to the negative 2. So you had gotten 1 over 15, and then it would have been a positive 2, which then would have been 1 over 225. And then 20 squared would have just been 400 because 20 times 20 gives you 400. All right, so now we're going to look at applying properties of integer exponents. So we're going to complete this equation. So we know that repeated multiplication turns itself into exponents. So we know that the number we're multiplying, in this case 3, becomes the base, and the exponent is how many 3's you have. So we have 1, 2, 3, 4, 5. So our exponent becomes 5. Now, if I take 4 of those 3's and put them in parentheses, and then leave the extra one out, this right here becomes 3 to the 4th power, and this here becomes 3 to the 1st power. And I know from before, since these two pieces are the same, look at right here, I know that regardless of what I do, I know the associative property allows me to move these parentheses around. So since I have 1, 2, 3, 4, 5 3's, I know that this and this are equal. So these two things actually still give me 3 to the 5th power. Now if I move and I split up the parentheses, I have 3 to the 1, 2, 3 third power times still 3 squared, so I have 3 cubed times 3 squared. Well, I still have 1, 2, 3, 4, 5. Okay. It's actually going to give me 3 to the 5th power. Right, so what do you think we would get then if the equation is 5 squared times 5 to the 5th? Well, if you notice a pattern here, we take the exponents and we actually add them together. So in this case, we had 3 to the 4th power times 3 to the 1st power, which gave us 3 to the 5th power. Here we had 3 to the 3rd power times 3 to the 2nd power. 3 plus 2 gives us 5, so our answer was 3 to the 5th power. So completing this equation here, we should end up with 5 to the 7th power. So I want you to write a general rule for the result of a to the m power times a to the n power. So it's just like what we did before back here with our negative and 0 powers. So we made a general rule, 1 over a to the n. Okay, so a to the negative n is going to turn out to be 1 over a to the n, and anything to the 0 is going to be 1. So on your own, I want you to write a general rule for what a to the m times a to the n is. How could you explain it to somebody in very general terms, what you would do to easily solve this problem? All right, so now that worked on when you're multiplying numbers with exponents. Now what happens when we're looking at dividing numbers that both have exponents, or the same numbers with exponents? So here I have 4 to the 5th divided by 4 to the 3rd. If I actually write it out in its repeated multiplication, and remember my rules when I'm dividing, I can cancel out. So for every 4 that I have on top, I can cancel 1 out on bottom, as long as I have that many. So I can't cancel out that last 4 because I don't have 4 4's on the bottom. So I should say for every 4 I have on the bottom, I can cancel 1 out on top. So I have 3 on bottom, so I can cancel out 3 on top. What I'm left with is 4 times 4, so I end up with 4 squared. Right? So let's try this again. I have 6 to the 8th, and I have 6 to the 3rd, and I end up with if I write it out, it's 6 times 6 times 6 times 6 times 6. That's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Cancel each other out. So here I'm still left with 1, 2, 3, 4, 5. So now here I have 6 to the 5th power. Is there any connection that you can make between the exponents you originally had and your new exponents? So the exponent I originally had and my new exponent. I want you to take that and make a general rule for what a to the m over a to the n would be. So you should have found that the connection between the exponents was that if you subtracted the exponents, you got your new exponents. So for a over m, or a to the m over a to the n, you are going to get, it's going to give you a to the m minus n. Right, so anytime that you are dividing numbers with exponents, they have to be the same number. Okay, so this has to be a 6 and a 6. It can't be a 5 and a 4. Okay, so the same bases with exponents, you can take those exponents and subtract them to get your new number, your new exponent. Moving right along. So now we're going to complete this and we're going to look at multiplying. So we have 5 to the third to the second. So we have 2 exponents here. So that means that we're taking 5 to the third and we're going to spread it out. So it actually means 5 times 5 times 5, and now we have to square that. So that means that not only do we have one of these, but we have 2 of them. So we have 5 times 5 times 5 times 5 times 5 times 5, because that's what squared means. You take whatever is in here and you do it twice. Well, if we look at this, we notice that this is just repeated multiplication again. So we have 1, 2, 3, 4, 5, 6 fives. So this becomes 5 to the 6th power. All right, so let's try another one and see if we can find a pattern. So I have 7 squared to the 4th power. So I write it out. 7 squared means 7 times 7. And I take that to the 4th power. So now that goes to 7 times 7 times another 7 times 7 times another 7 times 7 times another 7 times 7. Again, it's repeated multiplication, so I get 1, 2, 3, 4, 5, 6, 7, 8. I get 7 to the 8th power. Take a look, see if you can find any connection between your original exponents and your new exponent. Okay, so you should have found that when you have a number with an exponent taken to a power, that you can take those exponents and multiply them. And that will give you your new number in exponential form. Okay, multiplying those 2 exponents will give you your new exponent. Right, so we're going to try 3 of these. You have 8 of them in your notes, and we're going to go ahead and just do 3 of them. So 12 to the 4th power to the 6th power. What do you get when you do this? I want you to try it and then check your answer. 12 to the 4th power to the 6th power. I know that when I have two exponents, I can multiply my exponents, so I can take 4 times 6, that gives me 24. So I know I will end up with 12 to the 24th power. You can check. That's correct, 12 to the 24th power. Let's try another. Now I have two numbers with the same base. They both have exponents. So I can take those exponents, and if I look back in my notes, I know that I can actually add those exponents. Okay, so you should have found that you can add those, so you end up with m plus n. So I have 2 plus 4 is 6, gives me 9 to the 6th power. Check our answer. It's correct. All right, so here I have 12 to the 22nd power over 12 to the 4th power.